that the reward is not just directly tied to the current action or one action. What gives you the reward is the sequence of actions you made earlier, and that somehow affects the reward. So think about a gameplay. What you just click next, left, right, up, down, that doesn't determine the score. You have to make many moves to do the right thing to get some score, and that's what makes it so difficult. So in other words, we do not know which action was responsible for a certain reward. And then the question is, how can you tell which was a good and which action was good and which action was bad? And how can we reinforce the good actions? So that means we need a framework to connect the rewards to past actions, not just the current action. And if you think about the causality, the information has to flow backwards in time. We have to give credits to previous actions from the reward we get later. So that's called the credit assignment problem, and this is the difficult part. And we need some sort of mathematical framework to deal with this difficulty. So let's think about a simple example. So here we have a maze, and the goal is to enter at start and then escape to goal as soon as possible. And we are not going to do supervised learning. We'll just let the someone or the agent play this game or try to escape it, and let the agent to figure out what would be the best move. So in this setting, state could be thought of as the agent's current location, or you could also think of it as the image, assuming that the location of the agent is displayed here. And the actions could be up, down, left, right. We move one block at a time. And the reward could be set as minus the time taken to escape from the maze. You want to escape as soon as possible, and that means time taken is basically the negative. That could be considered as the negative reward. So if you put some numbers, it would be something like this. The states could be something between 0 and 28. Each number corresponds to a state. And actions, there are 4 possible actions, so we can assign numbers to them: 0 for up, 1 for down, 2 for left, and 3 for right. And reward could be -1 in each time step. So if you take longer, you'll get more minus reward, which is a bad thing. So to maximize the reward, you want to escape as soon as possible. And again, you want to design an agent that tells you what to do to maximize the cumulative reward. So this agent is essentially going to be a function that takes the current status as the input, and you want the agent to calculate the best action so we can make the best decisions. So what's going to happen is something like this. We are going to start at here, 0, and that state 0 is going to go to the agent. So that's a function, and that function is going to generate an output, action 3. So action 3 corresponds to moving right, and that action is going to change the current status to 7, move from 0 to 7, moving right. And since 1 time has passed, reward will be -1. And in the next state, we start at 7, and that goes into the agent. So the state 7 is the input, and it's going to generate action 3 again, which is again move to the right. And then the reward is going to be -1 again, and the state has changed to 8. And 8, again, that goes to the agent. Action 0, which corresponds to up, is generated. So go up. So reward would be -1 again, and the state will change to 1. So this process will repeat until the game is finished. So if you think about this game, no matter what you do, the reward is always -1. So just from the immediate reward, you cannot tell which was the good one, which was the bad one. You can only tell after finishing things. And once you finish things, as I said earlier, the information has to flow backward in time. So let me explain what that actually means. So let's say we played this game many times, and from the data, you can kind of see that state 27 is actually very good. If you arrive at 27, you're nearly done. So that means you can give high value to this state 27. And moreover, we can also learn that moving right, which is, I believe, action 3, is actually a good combination with state 27. So that means we can assign high value to this pair, state 27 and action right. And we can repeat the same thing for 26. So we know that state 27 is a good one, and state 26 can easily lead to state 27. That means state 26 is also good. So we can assign high value to this state 26. And moreover, similarly, we can also assign high value to this pair, which is state 26, and move to the right. That'll lead me to 27, which is good. So from knowing that 28 is a good thing, we can infer that 27 is a good thing. And that also tells you 26 is good, and 26 plus moving to the right is good, and so forth. So by repeating this process, we can basically assign numbers to each state, and also, or probably assign numbers to each state and action pair. And later, that is going to tell you what to do. If you know which is good, and then we know what to do. So that's what I meant by the information has to flow backward to be able to train this agent. So that's the bottom line, or the main idea of reinforcement learning. So that is the concept, and now we have to deal with the mathematics, which is going to cause a lot of headache. And again, this really involves a lot of definitions, and I don't have really time to go through everything rigorously, so I'll just kind of skip things. So let's see if you can manage that. So definition number 1, random variable. So it's a variable whose value depends on the outcome of a random phenomenon. So an easy example is, you can think of a dice rolling. So this capital X is a random variable from dice rolling. In that case, the probability that X will be 3 is 1/6, right? And the probability that it'll be 1 will also be 1/6, and probability that it'll be 7 would be 0, because if you have a dice, the possible outcome is only between 1 and 6. And the random process, you can basically think of it as a time series or a sequence of random variables. So an example is accumulated sum of a dice rolling. So if you, at time t, the probability that it'll be larger than the previous value by 3 would be 1/6. I mean, since this is the accumulated value, this is basically saying the dice rolling would result in number 3 at time t is 1/6. So you can think of a random process as a sequence of numbers. And here we have the capital or uppercase letter, and that means that X and Y, capital X and Y, these are random variables. These are not numbers. These are just representing, you can just think of as an event that is not realized yet. We don't really know what it is. And lowercase means that it's actually a number. So this small x, it could be 1 or 2 or 3 or 4 or 5 or 6. And this capital X, again, this is not a number. This is just an event. And the event outcome could be 1 or 2 or 3, and the probability, there will be corresponding probability for each possible outcome. And here comes an important one. There's a concept called Markov process, which is a kind of random process. And this Markov process is a special type of random process, which does not have any memory. So that means the future probability is determined by its most recent value. So it's a formal representation is given here. So the future state for this the probability of future state being something given the right before the past state is the same as the future state of being something given the entire past states. So knowing all this is equivalent to knowing just this, and that means knowing this is actually enough, and the past values doesn't really matter. So in other words, the future is independent of the past given the present. If you know what happened now, the future is not going to depend on the past as long as you know what happens now. And for a Markov process, we can define something called state transition probability matrix. So this P of ST equals 0, that means the probability of state at time t equals 0. And let's say there are 3 possible states, 0, 1, 2, then we can define something like this. So each of these corresponds to the possibility of current state being 1, 2, or 0. And here we have the possibility of past state at time t minus 1 equals 0, 1, and 2. So that will affect the future probability, and that relation is determined by this matrix right here. So this matrix is called transition probability matrix. So this P21 basically tells us the probability of next state being 2 given the current state of 1. And for example, P22, this is basically the probability of next state being 2 given the current state of 2. And to make it more concrete, let's think about an example. So let's say that 3 possible states are sunny, rainy, cloudy. So we're talking about the weather. We're talking about the weather transition. And PCR, this would be basically saying the probability of tomorrow being cloudy given that today is rainy. And PCC would be the probability of tomorrow being cloudy given that today is cloudy. So this is basically relating the weather today and tomorrow, or the weather yesterday and today. So one thing I would like to, let me just skip this slide, it's kind of too much. So here we have an example of a weather transition matrix. So the probability of tomorrow being sunny, given that tomorrow and today is sunny, that's 0.7, and we have all the numbers. So if today is sunny, the tomorrow has 17. So today is sunny, that means this is 1, 0, 0. Today is sunny, that's a probability of 1, and it has 0 probability of being sunny, cloudy, or rainy. And the tomorrow weather probability could be obtained by multiplying with this transition matrix, and that tells us that the probability of tomorrow being sunny is 0.7, probability of tomorrow being rainy is 0.1, and probability of tomorrow being cloudy is 0.2. And to make sure that we understand this, let's think about a few more things. So what would be the weather after 10 years? So that could be obtained by calculating this. So we have 10 years that correspond to 3,655 days. So that means there will be 6,655 transitions. So that means we multiply with this matrix by that many times. And if we think that the weather prediction on 3650 days would be not really different than, this has to be 49 days. If we assume that these two are going to be pretty much the same, we can do the following substitution. So here, this is relating the weather probability between this date and that date, which is just 1 day away from each other. Oh, there's T minus is missing here. That's just one matrix multiplication. And assuming that this is basically the same as this, we can replace this equation by the bottom equation. So again, T minus is missing here. And since these are scalar numbers, we can just replace these by A, B, and C, do the same thing for here, and we can just solve this matrix equation. And that is going to give you A, B, C values of these. And let's see if this actually makes sense. So let's say if today is sunny and we multiply with this matrix, that is going to give you this. Today, let's say today is cloudy, rainy, multiply with this, gives you this. Let's say today is cloudy, multiply with this, and gives you this. So regardless of the weather today, the weather 10 years from now is going to be the same as this, which we can verify with two different methods. So again, this is just to give you an idea of what a Markov process is. Again, it's a sequence of random events. It's a random process, and that meets the Markov property, which is the memoryless property. Given the present, the future is independent of the past. Again, given the present. So to define a Markov process, we need two things. We need a set of states. For example, we need to know what possible weathers are: sunny, cloudy, or rainy. And we also have to have the state transition probability. If today is sunny, what's the probability of tomorrow being cloudy? Things like that. If we know all that, we can define a Markov process. And once we define a Markov process, then we can actually obtain, or we can actually get a sequence of that. And that's going to be, I mean, whether today, whether tomorrow, whether 2 days from now, something like that. And that was the Markov process, and we need to build upon this. So next concept we're going to talk about is Markov reward process. So this is something, a little bit of something, I mean, this is, you can think of it as Markov process plus some alpha. And that alpha here is a reward. So the state transition is going to happen just like we did here. And one additional thing is that with each transition, there's going to be some reward. And the reward is going to depend on the state. So we just have to add this thing. This is just a mathematical formulation. And we are also going to define something called discount factor, gamma. And this is to quantify the value of future reward compared to immediate reward. So this gamma is basically of scalar value between 0 and 1. And if it's 1, it means future reward is just as good as the immediate reward. And if gamma is 0, we don't really care about the future reward. So in practice, we use a scalar value that is slightly less than 1. So with that gamma, we can define a return, which is actually a discounted sum of reward from time step t to horizon, where horizon means basically the end. So we can add all these rewards with the discount factor r sub t plus gamma r sub t plus 1. And for 2 times away from now, we multiply with gamma square and gamma cube and so on. So if you get the reward in the future, that future reward will be discounted by this factor gamma. So one thing you have to remember is that the reward and return are different. Reward is what we get at certain time, and reward is basically a discounted sum of that. Return is like a sum right here. So RT is the reward, GT is the return. This may be confusing, but it's very important that we don't get confused with this. And later, we're going to talk about value a lot, which is basically the same thing as expected return, or you can think of as expected value of return. So let's talk about that value thing. What we really care about is we want to maximize the return. Although we're just talking about Markov reward process, this is something we want to maximize. So this is what we really care about. So this expected return is basically a function of S. It depends on the current state. So we can write that as a function of state. So V of S, state value function for a Markov reward process. And that you can just plug in the definition of g of t, which was this. And since this is a linear summation, we can split the first term versus the remaining, which is going to give you this. And this term right here is basically about the expected reward at time t given the current state as. So that's the function of s. So we can write that as a reward function, r, capital R of s. So this is about the immediate reward or the expected value of the immediate reward. And the rest, if you think about the definition of the return, this thing right here can be written as this. So there's a little bit of math, but let me just skip this. And if you just rearrange the equations a little bit, the original equation right here that comes from the definition turns into this one. This is basically saying that the value of a certain state could be represented as a sum of the immediate reward and the discounted sum of the future reward. And this equation is called Bellman equation. This is just saying value equals present value plus future value. That's pretty much it. The value equals what we get immediately and what we get in the future, discounted by the factor gamma. So to familiarize ourselves with this state value function, let's think about this. Since this S right here, there are finite states, so we can think about all possible S. So that means we can write multiple equations, the first one right here, and those equations can be combined as a matrix form like this. And this matrix equation can be rearranged a little bit, and that gives you, by doing a little bit of math, we get the matrix V. And if you think about it, this P is just the state transition probability matrix. Gamma is just the discount factor, and R is the reward function. So that means if we know the transition probability, and if we know the reward function, we can find the value of each state. That's what this equation means. And if you think about the reinforcement learning, knowing the value is what really important. So if you go back to the maze example, what really matters is knowing which state is good. So, and we have to assign good high values to these states and low values to these states. And if you know this P and R, then we can basically figure out the value. All right, so we have to build one step further. So we first talked about Markov process. Later, we talked about Markov reward process. And now we have to talk about Markov decision process. So here we have another thing right here, which is A, set of actions. So in Markov reward process, the reward was just given along with the state transitions. And the difference between Markov reward decision process and the Markov reward process is that the reward and transition depends on the action. That means what we do now. It's like what the player does in a game. What the player does in a game is going to change what happens next, and also it's going to change how much reward we are going to get. So we have one additional term right here. Action A, a set of actions. And again, the state transition probability is now going to depend on both past state and the action. And the reward is also going to depend on state and action. So now we have SAR. So with the Markov process, we only had S. And with Markov reward process, we had S and R. And with Markov decision process, we have S, A, and R. We're almost there. So this MDP, Markov decision process, basically requires an action at each state. And for that, we need an agent. We need to take the state and generate the action to actually make a Markov decision process. So that means we need some sort of function that takes the current state and generates the action, which we are going to call as policy. So the policy is a function that for a given state S, the probability of action being A. So that's pi A given S. This is the policy. And if you think about what this policy means, this is actually the agent. You give the state to it and get the action out of it. This is basically the agent. So that means trying to get an agent or trying to train an agent is essentially the same as trying to find a good policy. I mean, we can design an arbitrary policy. It'll just generate some actions. But what we want to do is we want to make a policy that'll choose the action such that the cumulative reward is going to be maximized. So that is our framework. Let me skip this slide. So earlier with Markov reward process, we had this Bellman equation, which relates which basically says value equals immediate reward plus future value. And with MDP, things depend on the policy. I mean, things depend on action, and action is coming from the policy. So we're going to add this notation pi right here. The value now depends on pi. And the reward also depends on action. That means it depends on pi. So this R of S is replaced by R of S comma A. And same thing goes here. This V part now has pi because it depends on pi now. And the state transition, this is the state transition probability, which also depends on the action, which is why we have pi of S in here. Again, immediate rear depends on action and hence on policy, and transition probability depends on action and hence on policy. So this equation is the Bellman equation for Markov decision process. All right, so we have this equation, and the question is, how do we find a good pi or a good policy using this equation right here? Our goal is to maximize the expected return by choosing a sequence of good actions, and this is equivalent to trying to find a policy that maximizes the value function, which is right here. So the optimal policy, which we're going to denote as pi star, is a policy pi such that maximizes the value function, which is a function of pi. So again, if you find this policy, if you find this optimal policy, that's pretty much the end of the story. So actually, the one way of reinforcement learning is to directly find the optimal policy pi star. And there are also many other ways as well. Okay, going back to this framework, this is what we are doing. We have an environment, and that environment is going to give state S and reward R to the agent. An agent is going to choose the action A, and this process is going to repeat. So what we have at the end is a sequence of this SAR. We have multiple SARs at time 0, time 1, and time 2. And given this data, we want to design a pi or a policy that maximizes the cumulative reward. All right, let's go back to the maze example and just think a little bit just to match things. So here, the state is again the number that represents the current location. And action could be between 0 and 4, where each number corresponds to up, down, left, right. And the reward was again is -1 at each time step. And the agent, we're looking for a function that takes the current state and generates the good action. So it's going to look something like this. We start at S0 equals 0 here, and we're going to choose action 3, which is right. And we have reward of -1. And that gives you S1 of 7. And we are going to choose action 3 again, which is going to the right. And again, we get reward of -1. And we are now at state 8. And we are going to choose 0, which is moving up. And we again get reward -1. So this is what we are going to get at the end. And this is pretty much what we need for the reinforcement learning. So again, the agent is essentially a function. It could be a policy function that takes the state, determines the action probability given the state. So if you have this thing, this is pretty much the end of the story. And there's also another way, which is knowing the state action value function. So what I'm saying is, one of the things we talked about earlier was, if you go all the way back to here, we know that state 26 combined with moving to the right is a good thing. I mean, state 21 combined with moving to the right is not good, but state 26 moving to the right is a good thing. So we can basically give high scores to that. And that's something we're going to call as state action value function, which is defined as follows. So for a given state and a given action, what is the expected return? And that is the state action value function. If we know this function for a given state, we just have to calculate this for all possible actions because the action space is finite. We can try all A's and then find the action that gives you the highest value, and we can choose that action. So if you find the state action value function, that's also pretty much it. So we can either try to find this policy function, or we can either try to find the state action value function. Either way, we can find the good actions, which is what we are looking for. All right, so let's go back to the Bellman equation. And this is going to tell us how to train our agent. So this Bellman equation says, for MDP, says the value equals present value plus the future value. And this is the important part. If the policy pi is optimal, then the following equation holds. So this equation is basically saying that the value, if the policy is optimal, then given the current state of S, there are lots of different possibilities. There could be different possibilities for each next state. And we can basically add the state action value for the next state with the weighted sum over the possible next states. That is going to tell you this future value. So let me try that again. So when you're given the state S, you're going to choose an action A. And then the state transition is going to occur, S from S prime, but we do not know what that S prime is going to be. There could be multiple possible S prime because it's a stochastic. And for each S prime you might end up, you can calculate the value of state action value. So this is basically calculating this Q pi at next state with the that is averaged over the possible states. This is weighted sum of the state action value. And the thing is, this thing depends on pi. And if the pi is not optimal, if you have the best policy, that means this weighted sum is going to equal the best one. So this you can choose many different A primes, and the best possible one is going to equal this. Let me try to make this a little bit intuitive. I don't have a very good explanation right now, but what I'm trying to say is if the policy is optimal, this future value is going to be the same as the value we get from the best action. If we have the best policy, the future value is the same as what we would get from the best action. That's what this equation is saying. So that holds only when the policy is optimal. So we can replace this part right here by this one, the best future value we can get among all possible A primes. And that means for an optimal policy, if our pi is optimal, this equation right here is going to hold. So again, the value equals present value plus the future value. And the future value is represented as this maximum of this, because we know that our action A prime is going to be the best, because this is for the optimal policy. This equation holds only if and only if the policy is the best or the optimal policy. All right, so this Bellman equation is going to tell us how to train things. We know that this equation is going to hold, and we can just rearrange this equation a little bit. That means this has to equal to 0. And conceptually thinking, if this is not equal to 0, that means we have some error. That means our policy is not really good. So any deviation from this condition could be thought of as an error. So let's define that error. And that error is going to be just defined as this term. But we're going to, this holds only for pi, the optimal pi, and we're going to define this error for just any pi. This is not for an optimal pi. This error will be 0 for an optimal pi, but this will not be 0 for non-optimal pi. So now we are going to train the agent in a way that could minimize this error. And if we minimize it, it'll eventually go to 0. And that means we have the optimal policy. So this E is basically the error we are going to choose. So let's say we start with some initial value of this, and we are going to update with this error. So we want to, again, we want to make this 0. So what we're going to do is we subtract this by the error, and we are going to use some sort of learning rate alpha, and we are going to subtract this error after multiplying with alpha. And we are going to repeat this process multiple times until it converges. So we're just hoping that by repeating this error, epsilon will eventually go to 0. So actually, that's a relatively easy iteration. Just we repeat this process and wait until the error goes 0, and we have the best policy. And I mean, then we have the Q function, state action value function. And once we have the state action value function, we know what to do at each given state. We just choose the action that gives you the best, highest state action value pair. Okay, so it sounds like it's pretty much done. But the thing is, this update applies to only certain S and A. I mean, for all possible S and A, we have to do this until it converges for all possible S and A. And the problem is that the state action pairs, there could be so many different things. So in this maze example, we have 26 by 4, 27 by 4, that's a little more than 100 possible cases. So it's possible to do this. But if we have a very large environment, when there are many possible states and there are many possible actions, then calculating this QSA value, the state action value, becomes invisible. So we're gonna need some sort of different way of doing this. So that's where the neural network comes in. So far, this was not a neural network. This is just a function that's basically a scalar value for S and A. And the problem is that there are so many different possibilities, and that's why we are going to use the neural network. So the purpose of using a neural network here is we're going to use a neural network to approximate the true state action value function. The true state action value function requires so many possible things. So we have to deal with all possible cases, and that's difficult. So we're going to approximate the true state action value function using a neural network. With supervised learning, what we were doing is we try to approximate the true relation between X and Y using a neural network. That was a function approximation, and we are going to do a similar thing. We are going to approximate the true state action value function using a neural network. And that's where this term DQN comes from, deep Q network. The state action value function is called the Q function, and that we're going to approximate that Q function with a deep network. So this, hence DQN, deep Q network. All right, so we're almost there. So this is what we want to reduce, this epsilon. And this Q function is a neural network. That means it has multiple parameters. And let's denote those parameters as theta. So we can replace this Q pi by this. We now have additional term theta here and theta here. So this is just a parameterized function. And again, we want to minimize this epsilon. And when we say we want to minimize it, we want to minimize the size, not just value. Just to minimize it, we can send it to negative infinity. We actually want to send it to 0. So we can think of a loss function, which is epsilon squared, basically. And we can define a loss function like this, which we can minimize. We kind of want to make this as small as possible to find the Q function that is close to the true Q function. So how do we minimize this loss function? We just want to find the parameter theta that minimizes this loss function, which is what we have been doing a lot using gradient descent, right? So we have a loss function that is a function of theta, and our Q function is parameterized with theta, and our target function, this part right here, we are going to call it a target Q function, which also has this theta parameter. And we're going to play one trick, which I will explain later. But the thing is that we are going to treat this part, this theta, as a constant. We are not going to update this one. We are going to update only this part. This is our Q function, and this is our target function. And we're not going to update the theta in this part. And we're going to call it theta minus. And with this modified loss function, we can just calculate the gradient. So this is just the constant, and we have square. So if you take the gradient, we have this term multiplied by the gradient of Q. And once you calculate this one, you can just apply gradient descent update to update the parameters and repeat this process to make this loss smaller. And that is going to give you the theta value that is doing a better job at approximating the true Q value. And some of you might be wondering why we had to change the theta as theta minus and treat it as a constant value rather than variables. So short answer is we can try to minimize the original loss function without changing this theta as theta minus. And in that case, the true gradient is going to look like this. And then we can apply the gradient descent update to obtain the data parameter. But the thing is, it turns out to be slower. I mean, the convergence is going to be slower than the method we described here. And here's the conceptual reason. So this equation right here, coming from the Bellman equation, this is the basically this term is the Q function, and this term is the Q function that is coming from one step ahead. What I'm saying is there's a realization term, current reward, and we have the Q term for the next state. So this term is basically referring to the future thing, whereas this is about the current thing. We want those to match, but the thing is, this thing is coming from the future. And that means this term right here, RSA, this is something, let me put it this way. Earlier we said we want the information to flow backward in time. And that means we want to update the current value using the future values. And that's why we do not want to update this part, which is about the future. We just want to use the future values to update the current value instead of updating both. If we update both, the information is not flowing backward. The information will be flowing bidirectionally. And instead of that, we're going to fix this. And there's another way to interpret this, but I guess I can just skip this part. So by doing so, we can train a network. All we need is just this. And algorithmically, that's pretty much it. We just have to update this Q function to train a neural network, and that's pretty much it. But in practice, we have to have a few more things. One of which is, how do we generate these things? We need these to generate the Q function, and there are a few more other things. So let's think about some actual scenario. So we're going to start with an agent that is not trained. So we can generate we can play multiple games and take a record of SAR and keep track of this, where these A's are coming from the non-optimal or untrained agent. We just collect these and use these to update the Q function. One important thing is, if you just do it, the agent will make the same decision all the time, whereas we want the information from all possible actions. So for that reason, we have to explore things. We do not want these actions to be just deterministic. We have to give some randomness to it. And the simple solution to that is, with some probability epsilon, we can let the agent choose a random action instead of choosing the best action it thinks. And this is not so important. I'll just skip it. And we just put that thing together. This is pretty much it. And if you just write this as a code, that is going to give you the agent that can make the best or optimal action at a given state. All right, that's pretty much it. I know that I was going really fast and that was really too much for you. I totally understand that. And the reason why I'm doing this, whereas despite the fact that I know that this is too much, is that this is going to be overwhelming today, and it is going to be overwhelming later when you learn it again. I mean, I'm sure you will do is give you an overview of this, or give you just a little bit of feeling of what a reinforcement learning is. So hopefully when you see it next time, it'll be less overwhelming. So I do not think that I was able to make you fully understand this, but what I'm hoping is, just by listening to today's lecture, I hope that next time you listen to it, you'll be able to understand more. All right, that's pretty much it. So I guess I can now take some questions, starting with the earlier ones. Are there other types of machine learning beside 3 as well? Well, good point. Mainly, people think there are these 3 types, and there are some types of learning which aren't so clear whether it belongs to this, or this. In those cases, well, people trying to fit those into this, I guess my answer is, still people like to think that these 3 are major types of machine learnings. There are a little bit of something that's unclear, but we could still fit those into these, although it may not fit 100%. All right, do you have any other question? Everyone is overwhelmed too much? I mean, we already did it, right? We already had the RNN exercise last Thursday. And on Thursday this week, we are going to give a try with the reinforcement learning. We are going to try some simple examples. Okay, if there is no more question, I guess we could just finish. And as I said earlier, on Thursday, we will actually go through the collab exercise on reinforcement learning. All right, bye everyone. I'll see you on Thursday. Thank you.